Troubleshooting is one of the most challenging parts of an operator's job. The operator's know-how and experience are really put to the test when process problems arise. When a problem occurs in a process, there's a lot riding on how an operator responds. A process problem can have a wide range of effects, including products that don't meet specifications, final products that can't be sold, equipment that's damaged or destroyed, and most importantly, workers being injured on the job. To avoid these effects, operators are often called on to troubleshoot process problems. In this unit, we're going to introduce some of the basic concepts associated with troubleshooting a problem in a process. We'll also look at an example to see how some troubleshooting techniques can be applied. This menu offers a pretest option. If you want to take the pretest, you must select it now. During process operations, problems may show up at any time and anywhere. Some problems are as simple as an abnormal temperature or flow rate that can be corrected by a minor adjustment. Other problems are not as easy to identify and correct, especially when the cause of the problem is somewhere outside of the process. However, regardless of the cause, operators are responsible for zeroing in on problems whenever they occur and bringing things back to normal. A good way to ensure that the proper actions are taken in response to a process problem is to follow a troubleshooting procedure that is both systematic and logical. In simple terms, troubleshooting is the process of detecting a problem, determining its cause, and taking corrective action. For our purposes, we'll divide the troubleshooting procedure into 5 major steps. The 5 steps are identifying the problem, taking preventive action, determining the cause of the problem, correcting the problem, and returning the process to normal operation. The first step, identifying the problem, includes recognizing a problem and observing its symptoms. To perform this step, an operator can use many different sources of information. The first step, identifying the problem, includes recognizing a problem and observing its symptoms. To perform this step, an operator can use many different sources of information. Alarms and annunciators may indicate abnormal conditions. In some cases, a process shuts down automatically when certain abnormal conditions occur. In addition, during routine inspections, an operator may detect a problem. One sign that an operator might notice is a process variable indication that is not within its normal range. In many cases, a problem has more than one symptom or indication. In any case, however, any unexpected change should be investigated. Once a problem is identified, the next step is to take the immediate preventive actions necessary to keep it from becoming worse and causing injuries or equipment damage. For some problems, you may have to initiate an emergency shutdown. For others, you may need to switch the process or a component from automatic to manual control. Or you might have to bypass a piece of equipment or a part of the process. Before you take any actions, you have to consider the possible effects of the problem and your actions on other personnel, processes, and the product that's being produced. For example, you may need to notify personnel in other processes that there's a problem that could affect their operation or their safety. In some cases, it may be necessary to sample and test the end product. The test results may indicate that the product is of acceptable quality to sell, that the product requires further processing, or that the product must be disposed of. After the appropriate preventive actions have been taken, the next step is to determine the cause of the problem. Determining the cause of a problem is essentially a process of elimination, separating factors that are not causing the problem from those that might be. This may involve considering a number of factors. For example, is the change abrupt or gradual? Is the problem intermittent or constant? Have there been similar problems in the past? Did the problem occur while the process was in a steady state condition? Or was the process being started up or shut down? Answering these questions can help determine the cause of a problem. To do this, operators must fully understand the process. It is difficult to figure out what's wrong with the process unless you know how the process normally operates. During this troubleshooting step, an operator may need to refer to sources of information such as process diagrams, lab test data, equipment history records, incident reports, and operating logs and SPC charts, both of which can show trends in processes. These sources may help locate the cause of the problem. Other operators can also be a source of information. They may provide information that can help in troubleshooting. After the cause has been determined, the next step is to correct the problem. Correcting a problem can include changing set points and repairing or replacing equipment. In many cases, correcting a problem requires the assistance of maintenance mechanics or instrument technicians. After corrections have been made, the process can be returned to its normal operating condition. To return a process to normal operation, it may be necessary to reposition valves, switch the process back to automatic control, or adjust process variable set points to allow for a change in performance. If the problem has affected other processes or units in the plant, it's important to let them know that things are back to normal, so they can make adjustments at their end. Troubleshooting is usually based on a process of elimination, that is, separating factors that aren't causing the problem from factors that might be causing the problem. There are several ways that the process of elimination can be applied to troubleshoot problems. For example, one way to rule out individual components is to conduct input-output tests. To do this, you have to be familiar with the normal values of process variables. You can then check the process variables to determine the condition of the process entering the component and its condition coming out. For example, if the inlet temperature for a heat exchanger is okay, but the outlet temperature is not, then there must be a problem in the heat exchanger. The input-output method can be used to eliminate one component at a time as a possible cause of a problem. A similar method can be applied on a larger scale through an approach we'll call bracketing. The goal of bracketing is to narrow down the location of a problem to a certain process or part of a process. Once you establish the boundaries of the problem, anything upstream or downstream of these boundaries is eliminated as a possible cause. As an example, this illustration represents a process that has two separate trains. The equipment in each train is the same, and both trains process the same feed material. The problem is that the quality of the final product is off-spec. Since the product leaving one train is on-spec, the product leaving the other train must be off-spec. Bracketing has narrowed down the location of the problem to a single train. Another process of elimination method is to check the components in a process one at a time in sequence. This method is called the serial method, and although it is logical and effective, it can be very time-consuming. We'll use this process to see how the serial method works. The equipment in the process includes a steam heater, a reactor, a distillation tower with a reboiler, an overhead condenser, an accumulator, and a product cooler. Feed materials that enter the process are heated in the steam heater and then sent to the reactor. The product that leaves the reactor flows into the distillation tower. The desired product boils off and flows into the condenser. In the condenser, the product becomes a liquid, which is stored in the accumulator. From the accumulator, the product flows into the product cooler, where it is cooled before it leaves the process as a final product. In our example, an analysis of the final product indicates that there is water contamination. This contamination could occur in many places. The steam heater and the reactor both use steam to heat the feed materials. The reboiler uses hot water to heat the materials in the distillation tower. The condenser and the product cooler both use water to cool the final product. We'll start the serial testing at the beginning of the process, at the steam heater outlet. Test results indicate that there is no water contamination at this point. The outlet of the reactor is sampled next. Again, no water is found. The sampling continues until water is found. In our example, water was found in the sample taken from the outlet of the product cooler, so the contamination is from the product cooler. In some cases, you can eliminate possible causes of a problem faster by using a method called half-splitting. This method splits the process in half and reduces the remaining number of possible causes by half. We'll use a reflux control system for a distillation tower to show how this method works. We'll start by looking at the system. In this system, an accumulator contains liquid that is returned to the tower as reflux to help control the temperature in the tower. With this system, the accumulator level controls the flow rate of reflux to the tower, which in turn controls temperature. The system consists of a transmitter, an indicating controller, an electronic to pneumatic or I to P converter, and a control valve. The transmitter produces an electronic signal that represents the accumulator level. The controller receives the signal from the transmitter and produces a corrective output signal. The I to P converter converts the electronic signal from the controller to a pneumatic signal, and the air-operated control valve regulates the flow of reflux to the tower. In some cases, you can eliminate possible causes of a problem faster by using a method called half-splitting. This method splits the process in half and reduces the remaining number of possible causes by half. Testing the output signal from the controller splits the system in half. If this signal is at the correct value, we've ruled out the transmitter, the controller, and the line between them as possible causes of the problem. If it's not correct, we've ruled out the I to P converter, the control valve, and the line between them. In this example, the output signal from the controller is correct, so the next step is to split the remaining two components in half by testing the input signal to the control valve. If this signal is correct, we know that the control valve is the problem component. If the signal is not correct, then the problem is in the I to P converter. In this example, the input signal to the control valve is correct, so the problem must be in the control valve. In the example, the desired test points in the control system were all convenient and accessible. Actual processes may not be easy to split, and test points may not be easily accessible. The rigid demands of a troubleshooting method may have to give way to practical considerations of how the process is laid out. In this topic, we introduce some of the basic concepts of troubleshooting as they apply to process operations. We also saw how a process of elimination can be applied to troubleshoot a process. Now try some practice questions on this material.